Hello class, welcome back. We're beginning our new unit, Unit 3, Earth Systems and Resources. Starting off talking about Earth science concepts and the formation of our planet and how it changes based on plate tectonics and those interactions. To begin with, we'll talk about Earth formation as a very brief, not detailed at all overview, but essentially 4.6 billion years ago is the best estimated age of our planet based on its formation. The Big Bang determined the distribution and abundance of all existing matter in the universe here. And so that kind of started this formation process, everything unfolding here. The Earth is composed of these big plates, and we refer to those as tectonic plates. And they move and shift at about the rate of your fingernail growth, which is a good analogy. So about 2 to 3 centimeters per year. So the animation over here is simply showing from like 250 million years ago all the way to the current kind of distribution of continents on the planet based on plate shifting and separation. So we can get, as we're seeing right now, like more of a distribution for what we see in the world today, and understand that that wasn't always the case. The layers of the Earth structure itself is formed by kind of different layers as we go deeper. So we have like the crust is this outermost layer, the lithosphere right underneath, and then the asthenosphere. Those are going to be some of the major ones that we really talk about in this class. But basically, you need to understand that the Earth's surface is the lithosphere and the crust on top. That that makes up our tectonic plates. So these two structures kind of form plates together, the crust and the lithosphere. The asthenosphere is this kind of partly melted liquid rock or magma. It's this kind of, semi-solid, partly melted area that kind of helps to push and move the plates that sit above, so the lithosphere and crust. So these two things make up our plate, and underneath we get some convection currents moving the plates around. And that's what we're getting into here. So what causes plate movement? Why aren't they just static? Why don't they just sit there? Convection currents in the mantle and the asthenosphere, which is just below that, really kind of push those plates forward. So we have this convection action of this rising heat and the forces that get pushed up against the bottom of the plate. Since they are not able to just keep pushing their way through the plates, they run along the surface and pull back down as they cool, and we get this convection kind of process circulating right here. So you can kind of see this unfolding. These are your convection currents, and in doing that, it is slowly pushing these massive plates that are composed of the lithosphere and crust apart. So types of plate contact. How do these plates interact? We have a good draw it here, so we want to make sure we have a good diagram for you in your notes so you can reference that. This is really one of the key concepts in tectonic plates is the types of movement. So this is really key. Divergent plates are going to move apart. They diverge. They separate. This occurs from that same convection current action where we get them pushing up and then the plates on their boundaries start to separate. We see this primarily in ocean plates, so we see seafloor spreading. When they spread apart, this partially melted rock or magma comes through and creates new ocean crust. It can also form like underwater ridges, rift valleys, by pushing up and cooling in the bottom of the ocean, forming these little underwater mountain ranges essentially. Volcanoes and earthquakes can also occur at these plate boundaries as well. The next type of plate interaction is convergent boundary, converge, come together. We see when plates come together, one is going to typically slide underneath the other, and this is referred to as plate subduction. So what we have here is the subduction that's occurring, all right? So this is plate subduction right there. This can create volcanoes, island arcs, mountain ranges, and earthquakes. So we see a lot of this type of interaction on plates that are on the other end of this. So in one spot, if the plate is separating, is diverging, so convection currents are kind of doing this. This can separate, but somewhere out over here, we're going to get this kind of interaction, a convergent plate, and one's going to push below another. Any plate movement can lead to those earthquakes, but this ultimately causes one level to rise up, and as this rises up, this is where our mountain ranges form. The next thing is transform fault. Transform fault boundaries are slipping plates that are moving kind of laterally next to each other. So the pressure of these plates pushing together, one moves kind of up, one moves kind of down. They get stuck, and they kind of, once the pressure builds up so much, they kind of move just a little bit. That causes this tremendous release of stored energy, which are the big earthquakes that form. The next thing that's a labellet, and you'll get this from me. So this is going to be an in-class one here. All right. So there's a lot of stuff going on in this map. But ultimately, what I want you to see is that red is our convergent plates. All right. So these are moving together. The blue arrows are divergent plates, and orange is transform faults. So we should be looking for those three things. We'll start with transform fault. You can see the San Andreas fault, one of the most common ones that we'll talk about as far as the North American transform fault plates. And right along this coastal region in California, this is where we're familiar probably with most earthquakes present in the United States. So this region right over here. Certainly there are other fault structures, but I think knowing our most local transform fault is good. Divergent plate boundaries, what I challenge you to see is where are the patterns, where do we see them? We see them all in blue, so all in this ocean. So we get mid-Atlantic ridges formed, East Pacific ridges, Indian ridges. So all these are formed based on plates separating, diverging from each other. And then these subducting plates kind of are on the borders of our continents for the most part. So if you see that, this is going to form some of those land structures, those island arcs, volcanoes. This whole thing is called the Ring of Fire around here in the Pacific. So all of this is formed from convergent plates that are subducting on each other here. So that's really kind of what we're seeing. We try to identify general patterns. And the last thing to point out is a hotspot. Hotspot like Yellowstone, where you get a lot of thermal activity with these geysers and mud pots and all the unique geological formations here. It's almost like if you just poked a hole straight through the lithosphere and crust right through the plate and kind of allowed a lot of that heat and gas to escape. That's almost a good analogy for these hotspots. So Hawaii and Yellowstone would be two of our big ones to note. One last note here that's of lesser importance, but really important understanding how we tie into the rock cycle is the cycling of matter between igneous, metamorphic, and sedimentary rock. So really, just as a side note, right, like understand that rocks have a cycle to them, that the process of uplifting to the surface, and then so we get uplift, we get weathering and erosion, compression, heat and pressure, subduct and melting, and cooling. All these things are going to cause the type of rock to change. And really, these forces of change are breaking things down, compacting them together, and it's causing these structures to change and become slightly different. So how this ties to our soil formation, we really talked about the idea of weathering and erosion relating to soil formation, and how this process, everything that's going on in the mantle, the movement of plates, these forces of heat and pressure, subducting and cooling, they're all leading to this uplift, weathering and erosion, which kind of helps support our soil formation.